Good afternoon, everyone. My name is Alice. Welcome to the webinar organized by PolyU CEE and HAIE Civil Division. Today's section, we will explore innovative approaches and emerging trends in civil engineering practice. Today, we have Professor Yin from the Department of Civil and Environmental Engineering of PolyU. He holds a PhD degree in geotechnical engineer from École Nantes in France. He has published over 300 SCI papers with an H index of 82 in Google Scholar. His research focused on soil mechanics, large deformation, numerical analysis, and the application of artificial intelligence in geotechnical engineering. Professor Yin's work focused on developing data efficiency modeling from soil property estimation by integrating uncertainty quantifications, multi-definite data fusion, and machine learning. By tailoring uncertainty quantification into machine learning algorithm and combining low and high fidelity data, the approach reduced data requirements while improving reliability. A user-friendly platform is also developed to facilitate the application model evaluation and illustration of correlations. And after Professor Yin's presentation, we will have Q&A section at the end of today's session. If you have any questions, you can type in the chat box. So without further ado, let's welcome Professor Yin.
Okay, okay, thank you so much. So good afternoon, everyone. So before the talk, I would like to introduce a little bit our department, CEE. So this is designed for you to know a little bit our department. So this is a CEE global recognition by different rankings, for example, Shanghai ranking, QS ranking, and the CEE of PolyU is well ranked, you can see. And so this is by Stanford University for the world's top 2% scientists, and in our department we have 26 scholars ranked. And this we have one academician, which is Professor Teng, also the president of our university, PolyU, and some other professors with Chanjiang scholars, which is a very high ranked and with high reputations in academic achievements. And this is some research achievements for some large grants, like theme-based research scheme, which you can see in our department. We had 4 theme-based research grants obtained. And some others big fund as well, like IIF, Research Impact Fund, and the Green Tech Fund, CRF, you can see. And this is some academic programs for students, for example, undergraduate program for bachelor degree, for a postgraduate program for master degree, and the research postgraduate program for MPhil and PhD. And this some outstanding alumni. You can see very seniors and well-known in our field, in the field of civil engineering in Hong Kong. And that's all. I will not spend too much time on this. And I will change to the practice of machine learning and geotechnical engineering, which I prepared. Maybe it's a little bit different as So one introduced just now, but is about data-driven. Okay. Okay. Well, let's see first what is machine learning. So you can see some examples. I'm sorry that you can't see, you can't hear the sound, but I will introduce very quickly. What is machine learning? You can see machine learning can generate music, can do the translation. Self-driving robot you can see in our daily life. Uh, and so this is also some other uh, application fields you can see also for scientific calculation. So let's see the machine learning drive machine to learn rules from data. So this is a basic concept. And this is just one example of machine learning neural network. Because machine learning, in fact, has different, so many different algorithms. So neural network is just one of them. And this neural work is inspired biology from the human being, for example, the brain of a human being, you can see. And mathematicians arrange all these neurons, so all these stars like neurons, and this branch between stars is a communication of information, and can be arranged in this way. So for different layers, and each layer we have different neurons. And so this is a typical figure you can see for actually on neural network. And just one example, very simple example. For example, if we have data X, Y, so we have a very simple data, and normally we can use Excel. So this is like a cut from Excel. So in your Excel, we can choose, for example, linear equation. We can choose different types of equation. If we choose linear equation, it means y equal to ax plus b, and the Excel can help us to find the value of A and the value of B. Yeah. And with a minimal error between data and this line, this found line. So in fact, this is part of loss function. So for example, the distance, or the summation of this distance, it can be a loss function. And optimization method is least squares method in Excel. So this process to find a formulation or if we define a formulation to find the coefficients of this formulation, in fact, is machine learning. So everyone is using machine learning, I guess. So everyone used Excel to interpret this kind of results. In fact, it's a machine learning process. So a very simple example. And complicated examples like ChatGPT, DeepSeek we are using for different purposes and with a large quantity of neurons and layers. Okay. And maybe some of you are not in geotechnical engineering. So what is geotechnical engineering? In fact, we are facing three different kinds of materials in geotechnical engineering. It's like clay, sand, rock. So clay is in microscopic pictures like this, very small clay particles made of clayey soils, and the sand, for example, the sand grains, and the rock, so like this. And from geomaterials to geotechnical engineering is the engineering structures or engineering construction happened in the soil or rock in geomaterials. And the geomaterials usually in natural environment, usually with part of air, part of water, or um, fully filled by water, which we call saturated soils. And this is some, if the design is not well, done, and we will have accidents on the geotechnical structures. And this is some typical geotechnical structures like underground space and as a railway foundation and MSW disposal. It's a artificial island, offshore foundation, offshore engineering foundation, and dam, for example. This is kind of earthwork. So all this belongs to geotechnical engineering. And what the machine learning can do for geotechnical engineering? Because we're not nowadays we're talking about digital twins for smart city. So digital twins for smart city, we have the physical world and we have digital world, and we have data measured from physical world to digital world. Then we can do some calculation or prediction to have the results of the prediction what will happen in the next 1 hour or in the next day, for example, and for buildings and structures, for underground structures, geotechnical engineering belongs to this area. And the machine learning, so I just summarized some applications of machine learning. For example, the optimization, how to use optimization for engineering practice. And machine learning can be used for image recognition, for geological reconstruction, for intelligent computation, for geotechnical agent like a large language model and data-driven, for example. So this is a practice of optimization. For example, if we have excavation and we have different soil models during the excavation, we can the optimization can give us the optimal model based on, of course, the measurements, the field observation, and then can calculate what will happen in the next stage. So this is a kind of prediction for next stage. For example, based on stage 2 to predict the stage 3, based on stage 3 to predict the stage 4. And image recognition, this, for example, if we have a picture of soil, then we can use deep learning, machine learning to do the segmentation, reconstruction, identification of morphology of soil particles in this way. And this is an example of geological reconstructions. If we have some boreholes and we can connect all these borehole informations together with more accurate information obtained using machine learning instead of conventional method we used before. And also for intelligent computation, for example, we have some PDE, like in finite element we use is based on PDEs. And if we use machine learning, we can have physics-informed neural network, for example. Physics-informed neural network is written as PINN. We can put PDEs into the arrow function as part of arrow function and to train the model. And then once the model is trained, then we use the trained model to calculate other cases, which is very fast. And the large language model as well for geotechnical AI agent in this way. So we can use different platforms like GPT, DeepSeek as a base, or some other large language models to get what we need for example, for geotechnical design. And we can also feed very specific geotechnical engineering textbooks or design codes inside, and then to get the specific geo AI agent, for example. This is one kind of work we are doing. And the data-driven modeling, if we have soil properties, so we want to get the mechanical properties of soils based on physical properties, then we can use many data and to uh, conventional way is to fit some formula equations, and if we have so many factors, influencing factors, then machine learning will give us better answer for this way. And also constitutive models as well. It's also a kind of data driven. So practice of machine learning, constitutive modeling of soils. This is what I would like to deliver today. And this work, in fact, is we have it's based on our project RGC, and carried out by some of my students, like Tong Zhang, graduated last year, and Yin Fujing also did part of supervision uh, together with me. So let's see the soil behaviors. For example, we have different soil behaviors like isotropy, structure, time effect, cyclic effect, small string stiffness, temperature effect, grain breakage, internal erosion, induced change of PSD, as water saturation degree, for example. All this will influence the soil behavior. And conventional modeling, we for each feature we will propose or we will add one or two equations, and each equation we will have one or two parameters to control. So you can see, you can imagine if we want to develop the model to consider all these features, then we will have so many equations and parameters, which is very difficult to use for practice. So practically, conventionally, let's say, conventionally we have some constitutive models developed during last decades up to very advanced constitutive models. And the equations or model expressions, mathematical equations, in fact, is based on data. In fact, it's fitted from data. And when we fit from the data, in fact, we already have assumptions because the data is not always smooth, or we can't account all factors in one set of data, for example. So this is already gap to ground truth. The ground truth is a reality. And also, if the model, advanced model with many features, as I said, so each feature will have equations and parameters. So the identification of parameters will be very difficult. So from theory to practice, it's a big challenge for engineers, especially. So what else we can do? So in fact, this is a statistician, Box George, very famous. He said essentially all models are wrong, but some are useful. So this is the work we are doing, trying to find or develop useful models or make existing models useful. So this is our purpose. So in this work, we try to develop or find useful models using machine learning, different from conventional modeling approach. So this is machine learning in quantitative modeling, and the state of art. We checked, and so for the technical engineer or civil engineering or geological engineering field, so the amount is very small. So that's why we are trying to. So maybe exists some very difficult challenges, and so we try to do something for this field. And the first thing we need to do is to establish the framework of data-driven quantitative modeling. It's like elastoplasticity. We need a framework of elastoplasticity, and then we can see some challenges and try to find solutions. Okay, so the framework, in fact, is made of 4 steps or 4 parts. So the first part is data set. It's like every problems of using machine learning. So we need data, and then we can choose suitable machine learning algorithm, because machine learning has so many different algorithms. And then we need a loss function, because in soil quantitative modeling, we have different terms like stress and strain or some other variables. So stress is KPA, for example, the order, and the strain is percentage or just 0.1, 0.2. So the order, the magnitude of values are totally different. Optimization algorithm and to update the parameters in machine learning algorithm during the training. So the data set from conventional laboratory tests or advanced laboratory tests as well we can use. And machine learning algorithm, we did a search in Web of Science, and we find the neural network is most of people choose the neural networks for this purpose, for this problem. And the loss function, we use the squared loss for regression problems. In fact, there's some other kind of loss, for example, the cross entropy loss for classification, which is not our problem. And the optimization, there's deterministic optimization or stochastic optimization. And the deterministic optimization, like gradient-based, this very fast, but will have local minimize. And stochastic can get global solution, global minimize, but large computational cost. And in machine learning, because we have so many tasks of optimization, so deterministic is currently is a good choice. And then, so we have the step 1, 2, 3, 4. So once we have the data set, so we choose suitable machine learning algorithm. We have the loss function and optimization to minimize the loss once. So this is a training process. And once the model is trained, it means all parameters in machine learning algorithm is obtained. And the model can be used to predict other kinds of tests. Okay, so the uh, the model, the trained model, is based on data. It's based on the real data. We didn't have specific equations, so there's no assumptions because specific equations we need. In fact, we made based on assumptions. So there's no assumptions made because we just use the framework. And the less parameters are once trained, and all parameters obtained. And so once we have the framework, we can feed the new data and can train and can be used. So no need to identify parameters. Okay, so once we have the framework, we can see some challenges. Here I just choose 3 challenges because there are so many challenges, not only these 3. So I choose this typical challenges like test dependent, which is a fundamental behavior of soils. And high fidelity data is too expensive because in soil modeling, we also always face the problem of data, limited data, and the reliability. Okay, so because of time, I introduce very briefly for each challenge and the solution. So if you are interested in some parts, so you just check with our publications, which will give you details. Okay, so for test dependent, so at the beginning we tried different machine learning algorithms. So all this we used, and finally we find the LSTM neural network, long short-term memory neural network, works well for our program. And so this is a typical scheme of LSTM. And so this input cell, so this LSTM cell. LST inside of LSTM cell, there's different types of calculations. And so this F means this calculation, TI means this calculation, O means this calculation. So there's different calculations made in each LSTM cell. And the whole structure is input cell, LS cell, dense layer, and output. And what we did, so we add something. So first thing is for different steps. So we add the links between steps. So the previous step will influence next step. Only add on the layer of LSTM cell. And so it's like this. So this is a LSTM cell. So this is input. And so step 1, step 2, step 4, step 3, step 4, for example. So the previous step influence the next step. So this to try to put the memory for the during the process. Okay, so this is just one example. And the second thing we did is the output. So here's the output. Okay, so this output will be used as part of input for the next step. So this output will be used as input at the beginning. So which is called feedback topology. And so this is also a kind of history. So the LSTM with feedback. So there's 2 modifications we did based on the conventional LSTM, and is found suitable for path-dependent soil behavior. So, so this is mathematical verification. So mathematical verification means we have the constitutive model, and we generate so many data. And we use some of data we used for training, and then some other data we used for testing. So these are testing results. So it means mathematically. So it's the model can represent, can reproduce the mathematical model. The second thing we would like to say is experimentally. So we collected so many experimental data for the cyclic behavior on Toyola sand, because Toyola sand we can find so many data in published articles. So this are only testing data. So it seems it's quite good, the prediction. Okay. And the second problem is that data is too expensive and limited, because in our practice, if we for the engineering design, we need CN5, for example, and to get CN5, typically we will use the soil samples. We will cut soil samples to carry out 3 or 4 tests. 3 or 4 tests based on results, we can get the values of C and phi. So only 3 or 4 tests on one soil. So the data normally is very limited. And in this case, how can we do? Because machine learning, we need, for the machine learning, we need many data. So how can we do? So we need to find, to enrich the data. So for this case, so we define high fidelity data and low fidelity data. So the high fidelity data is the real data tested in the lab. It was high precision, expensive, limited. And the low fidelity data is the data generated from numerical experiments or numerical calculations or some cost measurements. For example, we have stress strain model. We have the modified chemical model. We can give different stress passes to generate data based on modified chemical model or some other advanced models. Or if you do a calculation on flat element analysis, and in flat element for each Gauss point, we have stress strain information. And one calculation, we can get so many stress strain curves or data from all Gauss points. Or if we can also use DM to simulate the different tests or engineering structures as well. So all this data generated numerically is called low fidelity data because it's low precision, low cost. It's easy to do. And the conventional developed model, like modified chemical model, in fact, it has some experience, have some sort of theoretical backgrounds. So it's something useful. So that's why we try to extract or useful information in the past. So our strategy is use generated data to train a model first. So this model is like the first part, LSTM model. So low fidelity model training is called in this part. So we generated so many data, or we collected so many data generated numerically. And based on all this data, we train the model. And then we have the lab, the data from the lab tests, for example. And in the lab tests, results in lab tests, we give the input. The results can be, the results have the format of input and output. So we give the input to the trained model. Of course, the model will give us the answer according to the low fidelity model, which the predictive, for example, for the predictive stress will be, of course, different from the data we gave. So the predictive stress will be totally different from the high fidelity data, the stress in the high fidelity data. So this difference is called residual stress, for example. And we have all this residual information. We can change the residual model, the second machine learning model. And the predictive stress plus residual stress. It means the stress will be corrected by the residual part. So, which will give us high fidelity stress. And this second part is to fix the value. So it means, in fact, the first part give us the rule. So we learn the rule. We then learn the rule based on generated data. And the second part is to correct the value. So we have the rule and we have the value collected. So we can understand it in this way. And then the model will be, we can use the model. For example, here we use EVP MCC model to generate data, and we use experimental data of Hong Kong marine deposits, and for different stream rates. And this in fact, by the model. So this is real data. This is real data. And this is prediction by EVP-MCC. And the EVP-MCC for this OCR part is not so nice. Also for this part is not so good. And then our strategies is we use EVP-MCC simulations. So all these lines is used as low fidelity data to train the model. Then we have the rule of the EVP-MCC model, and then we use some of experimental data as high fidelity data. Yeah, in black. So this one, for example. And the rest is used to test. So this is data and the model. So this here we have two. So use different model parameters. So it means, so for the numerical part, even the parameter is totally different from the real soil. For example, the friction of the Hong Kong marine deposit is 30 degree, and we can use 40 degree, the friction angle 40 degree to generate data. And this once we have the high fidelity collection, the model can still be collected. So you can see. So the different parameters. So it's independent. The strategy is important. It's independent of the model parameters we used for the low fidelity parts. So this is an example. Of course, we can also put physical informed to have the model to be more, the generalization of the model can be better, be improved a lot. So because of time, I will not introduce detailing for this part. So this is, if you're interested in it, you can check our publication. And the challenge 3 I choose is reliability, because the soil, you can see, for the same soil layer, the soil behavior is not totally the same. And in the when we do the soil sampling from the same part of the soil samples specimens, the specimens close each other. The two specimens tested the stress strain behavior can also not be totally the same. So this is because the uncertainty, like spatial variability uncertainty. So this uncertainty, how to consider this uncertainty in machine learning based model. So for example, typically the neural network, if we use a neural network, and we have the neurons, we have the parameters between neurons. And all these parameters, once trained, is deterministic values. And there's one way is to give, instead of deterministic value, we give this distribution, like normal distribution. We assume normal distribution or Gauss distribution for each parameter. And then once trained, of course, the model will give us the uncertainty because of distribution, all this distribution. And the second way is to plot the information connections between neurons. For example, we have 100 links, 100 connections. So we can cut 15 connections and randomly cut 15 connections. And then we can change the model. So randomly means we don't know which connection will be cut. So we can cut one time to get one model. We can cut the second time to have the second model, which the place of connections cutted are not the same. So we can have, in this way, we can have 100 models with different places connections cut. And we give the data to train, and we can train 100 models. So if we have new input, we can use 100 models to get 100 results. And if we do the statistics, this gives us the information of uncertainty. So this is what we did. So we give randomly cut, which is called Monte Carlo dropout. And this is the results. So the results by 100 or even 1,000 models trained. So we put 1,000 results together. Of course, it will give us something like a bell instead of a line. Okay, so this is typical results. Okay. And the last question is, how can we use the machine learning based model for practice? So the constitutive model, how to use constitutive models for practice? Usually we use finite element. We implement the constitutive models inside of into the finite element code, and to simulate engineering structures. So in this way, if we just replace the conventional stress string model by the machine learning based model, the others kept the same. And we did the check. For example, we use modified chemical model to train machine learning model. The machine learning model based on modified chemical model represents the behaviors of modified chemical. And then we just do a very simple biaxial test to create this sheband. So this is a real modified chemical model, and this is data-driven modified chemical model, mathematically to verify the approach works or not. So you can see it's totally the same. So then we have other data-driven model can be used so mathematically is correct, that can be used for any developed machine learning based model. Okay, so because of time, I just introduce briefly our work. So the soil behavior, different soil behaviors, how to deal with these challenges. And so this is an unconventional way. Conventional way can also describe the soil behavior, can also be used for application. So why not choose this new approach as alternative? So this selected publications, and you can find some small or tool, let's say, developed by our group. Thanks for your attention.
Oh, thank you, Professor Yin. If you have any questions, feel free to type in the chat box. We will answer your questions. So first questions, we have questions from YC. So YC asks if the current AI technology can capture 3D images on a rock slope, and the model can analyze the discontinuous data and carry assessment on the stabilities. And if it is possible, can AI helps to determine with actual slope conditions where and how many long slope tiles shall be installed?
3D images of rock slope. Uh, I think the AI technology is to analyze the images. So we need a 3D image technology. For example, we have different angles of cameras, and we have CT device to get images. So first we need to have 3D images. Then we can use machine learning or deep learning to do the analysis on this. Yeah.
Okay. And second question is from YC. For rate dependent behavior modeling, would it be applicable to tunnel engineering where we adopt observational approach, where the convention monitoring data log from for the NATI
Yeah,
design? Sorry.
yeah, of course, yes, totally yes. Mm. Yes, because we have the model, model integrated FEM, so we can do the prediction and analysis for any kinds of structures.
And then Keith has a few questions. Oh, that's a bit long. The questions. Maybe I share his questions on the chat box. Sorry.
Yes, it's a very long question. Yeah. Mm, mm. Yeah, of course we can use first link. The on-site geotechnical data is very useful. And on-site geotechnical data based on which we can get soil properties. And soil properties, the soil properties can be used directly with conventional models, also can be used for machine learning based models as well. And how to ensure the sufficiency and reliability. It's a very good question. In fact, strategically, So we have the multi-fidelity strategy. So our multi-fidelity strategy, in fact, uh, is to solve this problem. So even the data is not sufficient, we can still get a good answer if we use the multi-fidelity, which I said just now, the low fidelity training and high fidelity training. And what I showed is two levels, low fidelity, high fidelity. In fact, it can be have 3, 4, 5 levels. So which we call the multi-fidelity. So not only two fidelity. Mm. And for the overfitting problem, we can always uh, avoid this problem by adding uh, localization term. So there's mathematically we can deal with this. Application, yes, experience, yes, yes, we're trying to develop a large language model, which I call your AI agent. And in this AI agent, we will incorporate many design codes, and we're trying to incorporate geotechnical or experience. Yeah, yeah. And this in fact I think need some uh, uh, we need more and more companies to integrate to work together for this agent. So I'm looking forward to work with you if you are interested in this.
Okay, thank you, Professor Yin. Any more